Hey everyone. So today we're going to be talking about section 4.6, which is all about related rates. And something kind of interesting about this section is it's all application. So there aren't really any new notes. We're just going to see a bunch of examples. So these are hopefully more real world examples that use implicit differentiation. So that's from section 4.5. And hopefully this brings a little more clarity to that section and gives you a little more appreciation for what calculus can really do. So in example one, it says that a 26-foot ladder is placed against a wall. If the top of the ladder is sliding down at 2 feet per second, at what rate is the bottom of the ladder moving away from the wall when the bottom of the ladder is already 10 feet away from the wall? So if you take a look at our picture here, the idea is that we have a ladder leaning against the wall here and it's falling. The top of the ladder is sliding down the wall at a rate of 2 feet per second. And they say that the bottom of the ladder is already 10 feet away. So in this problem, x would be 10. And they're asking how quickly is it moving away from the wall? So your first idea might be that it's going to be moving away at 2 feet per second. But it actually will not be moving away at 2 feet per second. So how could we solve a problem like this? So in our picture, we know that this ladder is leaning against the wall, and they do tell us that this is a right angle. So I need to relate all three parts of this triangle together, and that's going to be done using the Pythagorean theorem. So I can say that x squared plus y squared equals 26 squared. So that's because it's a right triangle, we can use the Pythagorean theorem here. And we want to know at what rate is x changing. So this is really asking what is dx, dt, or x prime, if you will. So I'm asking what is the rate at which x is changing? So that's the change in x with respect to time. Now we know that the ladder is falling at 2 feet per second. So this would be our dy dt, or y prime. And knowing that x is 10, we could actually find y. So here we have a bunch of variables. So if I wanted to, let's call this z. I could have an x prime, a y prime, and a z prime. And the idea is that I should know most of these, and I'm trying to solve for one of them. So I know that z right away, that's 26, that's given. I know that x is 10, that was given. Dy dt, or y prime, is -2. It's falling at 2 feet per second. Z prime, dz dt, does the length of the ladder change throughout the problem? As far as we know, no. It is a fixed 26 feet, meaning the change in z is non-existent, 0. So that just leaves us with two missing variables, y and x prime. So x prime is what we want, and if I had to guess, we're probably going to use y. So let's go ahead and solve for y. So I'm going to do that by plugging in 10 for x. So I get 10 squared plus y squared equals 26 squared. And I'm going to use a calculator to figure out what 26 squared is. We're going to have 100 plus y squared equals 26 squared, which is 676. So if we subtract 100, we're going to get y squared equals 576. So y is going to be 24. So the ladder is 24 feet off the ground. So now we need to find x prime, or dx dt. Now if you remember implicit differentiation, we kept getting these primes. So if I set up the problem again, using Pythagorean theorem, I've got x squared plus y squared equals 26 squared. And I'm going to take the derivative of this whole thing with respect to time. Time is the independent variable here. That means when I take the derivative of all of these variables, I should be getting primes afterwards. So the derivative of x squared is going to be 2x, x prime. The derivative of y is 2y, y prime. And the derivative of 26 squared is going to be 0. Now if I take a look at my left-hand column, I know all of these variables except for x prime, and I can solve for that. So this would be 2 times 10, so this is 20x prime, plus 2 times 24 times negative 2. 2 times 24 times negative 2. And this is all going to be equal to 0. So 2 times 24 is 48 times 2 should be 96. So I'm going to get that 20x prime should equal 96 if I move that over. Divide by 20. And I'm going to get that x prime is 4.8. So this means that the ladder is going to be moving away from the wall at a rate of 4.8 feet per second when it is already 10 feet away. And this is an example of a related rates problem. So we had to use implicit differentiation to set it up, but hopefully this is giving you a real tangible experience of like when we could use calculus. So some suggestions for solving related rate problems. This is where students tend to have some trouble because almost all related rate problems will be word problems, and those historically are the hardest problems in math. But honestly, they shouldn't be too bad as long as you can follow some steps. The first step is to sketch a figure if it's going to be helpful. So if they're describing a situation, it is probably going to be beneficial to draw that situation. Many times when you're getting started, the picture will be provided for you, but that's not guaranteed. So try to sketch out this scenario. Step 2, it says identify all relevant variables, including those whose rates are given and whose rates are yet to be found. So that's kind of what we were doing in example 1, where we had x, x prime, y, y prime, and then z and z prime. They weren't actually needed for the problem, but it doesn't hurt to have more information than you need. It says express all given rates and rates to be found as derivatives. So we need to find some way that everything is related to each other, and we need to take its derivative. Implicitly differentiate the equation, and then use chain rule where appropriate. That means make sure that we're getting the primes when we need to. And then they say substitute in all given values and solve for the derivative that will give you the unknown rate. And we're going to be following these steps on every example in this. So if you don't remember it, just keep watching these examples, and I would kind of say just imitate what I do when you're solving problems, because this method really, really does help. Draw a picture, identify your variables, figure out how things are connected, take the derivative, and then you're going to plug in and solve. So example 2, it says, suppose that 2 motorboats leave from the same point at the same time. If one is traveling north at 15 miles per hour and the other is traveling east at 20 miles per hour, how fast is the distance between them changing after 2 hours? So it does say draw a picture, label all variables in the picture as a function of time, x, y, and z, but then they're nice enough to just give us the picture. So step 1, draw the picture, we have it. So let's take a look at what variables we have. We've got x, and then we're going to have x prime. You could call x prime dx dt if you want the change in x with respect to time. You can call y prime dy dt and z dz dt. I would actually say that's probably the most common notation for related rates, but if you like the primes, you can stick with the primes. So we got x prime, y, y prime, z, and z prime. So let's see if we know any of these. It says that a boat is traveling north at 15 miles per hour. So that is y changing at 15 miles per hour. So y prime is going to be 15. And then they say that there's a boat traveling east at 20 miles per hour. So this would be the change in x, or x prime. And they say the boats have been traveling for 2 hours. So that should be able to tell us what x and y are. If you're traveling at 20 miles per hour for 2 hours, then you have traveled 40 miles. And if you're traveling for 2 hours at 15 miles per hour, then you have traveled 30 miles. So x is 40 and y is 30. So that leaves us with z and dz, or dz dt, or z prime. So again, north and east are perpendicular to each other, so this is a right angle. So we could say that the variables are related by the Pythagorean theorem. X squared plus y squared equals z squared. Now, you might not see it right away, but we can actually find z very easily by plugging in 30 and 40. And this is a 3, 4, 5 Pythagorean triple. So z is going to be 50. If you don't see that, I would say just plug in 30 and 40 for these variables, and you're going to find that z is 50. And I'm trying to find the rate at which these boats are moving away from each other. So that would be z prime. The distance between them would be the hypotenuse of this triangle. So if I use some implicit differentiation, so take the derivative of everything with respect to time, I'll get 2x, x prime, plus 2y, y prime, equals 2z, z prime. From here, if I wanted to, I could just go ahead and divide everything by 2. All the 2's will go away. And I can plug in here. I know that x is 40 and x prime is 20. So this will be 40 times 20 plus y is 30 and y prime is 15. So this would be 30 times 15 equals z is 50, z prime. So 40 times 20 is 800. 30 plus 15 is 450. And that's going to equal 50 z prime. So that's going to be 1,250 equals 50 z prime. So z prime will equal 25. And units would be miles per hour. So the boats are moving apart at a rate of 25 miles per hour in this problem. All right, so example 3, it says find the indicated rate given the other information. So it says that y equals x squared plus 2, dx dt is 3 when x is 5, and they want us to find dy dt. So fortunately, this is not a real-world example, meaning we don't really need to draw a picture here. We just need to list off what our variables are. We've got x, dx dt, we can also call x prime. It's all up to your personal preference. And then we've got y and y prime. So they want us to find y prime. So they tell us that x equals 5. They tell us that dx dt is 3. So with this alone, we can actually find y. If we just plug in 5, we get y equals 25 plus 2. So y is going to be 27. And now to find y prime, I need to take a derivative of this equation. The derivative of y is y prime. The derivative of x squared is going to be 2x x prime, and then the derivative of 2 is 0. I can say this is probably where I see the most mistakes when getting started. X in this case is a function of time, meaning that we're going to get that x prime at the end, and it takes a long time to break that habit because we are taking the derivative with respect to time. And from here, we can just plug in. We know that x is 5 and x prime is 3. So we get y prime is 2 times 5 times 3. And that gives us that y prime is 30. And that's all there is to that problem. So here we have an example, kind of like example 3. It says find the indicated rate given the other information. So it says that y equals x cubed minus 3. Dx dt is -2 when x is 2, and they want us to find dy dt. So our variables are x and y, and that means that we have an x prime and a y prime. So they tell us that x is 2, and x prime, our dx dt, is -2. So if we want to find y, let's just plug in. We're going to get y equals 2 cubed minus 3. So that should be y equals 5. And then to find y prime, we're going to take d dt. So the derivative of y is y prime. The derivative of x cubed is going to be 3x squared x prime. And then the derivative of -3 is 0. So from here, we're just going to plug in. Y prime equals 3 times 2 squared times -2. So if I'm not mistaken, 3 times 2 squared, that's 12, times -2 is -24. So our indicated rate, our y prime, is -24. So you might also notice that we didn't actually need to find y in this problem. And it's one of those things that better safe than sorry. I would rather find something and not need it than to need it and then have to solve for it later. But if you skip finding y, it's not going to be a problem. You could just find them as needed. All right, so Boyle's law for enclosed gases states that if the volume is kept constant, that the pressure P and the temperature T are related by the equation P over T equals K, where K is a constant. If the temperature is increasing at 3 Kelvin per hour, what is the rate of change of pressure when the temperature is 250 degrees Kelvin and the pressure is 500 pounds per square inch? All right, so we have two variables. We've got P and T. K is a constant, so I mean, that they could be 3 for all we know. It's not a variable, it is going to be a fixed constant. So they tell us that the temperature T is 500, the pressure P is 500, and they say the temperature is increasing at a rate of 3 Kelvin per hour. So that's our T prime is 3. And they're asking, what is P prime? So we've got our variables. T is 250, T prime is 3, P is 500, and P prime is what we want to know. So they also give us the relationship, P divided by T equals K, where K is constant. So this is where we would take our derivative implicitly. So using implicit differentiation, we have a quotient, so we're going to have to use our quotient rule. So remember, quotient rule would be bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Now, we absolutely can do a quotient rule. Well equipped to do that, not a problem. But I would say rewrite this to be P equals KT. It's just a little bit simpler for us. So if you are wanting to do the derivative here, we're going to take the whole derivative of everything with respect to time, which would be of lowercase t. I'm going to get that P prime equals KT prime. Now, I don't know what K is, except for, I kind of do. I know what P and T are, so therefore I know what K is, so I could say that P prime equals P over T, T prime. And honestly, that'll be the same answer you'll get if you use the quotient rule here. And if we just plug in now, that would be P prime is 500 divided by 250 times 3. So this is 2 times 3, which is 6. So our P prime is going to be 6. And that's pounds per square inch, PPI per hour. So 6 pounds per square inch per hour. Number 6, we got Boyle's law again. So it says Boyle's law for enclosed gas states that if the temperature is kept constant, the pressure and the volume of the gas are related by the equation Vp equals K, where K is again a constant. So it says that if the volume is decreasing by 5 cubic inches per second, what is the rate of change of pressure when the volume is 1,000 cubic inches and the pressure is 40 pounds per square inch? So our volume is 1,000, our pressure is 40, and our volume is changing. So our V prime is 5, and they're asking us to find P prime. So V is 1,000, V prime is -5 because it's decreasing. P is going to be 40, and then P prime is what we want. It's unknown. So in order to take a derivative here, we do have a product. So the product rule is pretty easy. We're going to say that the first function is V. So F prime would be V prime. Our second function is going to be P, meaning the derivative is P prime. And then we just cross multiply and add. So these guys plus these guys. So when we take the derivative, so we're taking the derivative of the whole thing with respect to time, we're going to get P V prime plus V P prime. And then the derivative of a constant is 0. And then from here, we just plug in. So it's going to be 40 times -5 plus 1,000 P prime. So 40 times, and this will equal 0. So 40 times -5 is going to be -200. Move that over, we're going to get 1,000 P prime equals 200. So P prime is going to be 0.2. So our pressure is increasing by 0.2 pounds per square inch. Or, yeah, pounds per square inch. So last example for this section, it says that a boat is being pulled towards the dock as shown in the figure. If the rope is being pulled at 3 feet per second, how fast is the distance between the dock and the boat decreasing when it is 30 feet from the dock? All right, so we know that this right here is going to be 30. And we want to know how quickly is this changing. So let's call this x, and we're looking for x prime. That's how quickly the boat is approaching the dock. Let's call this guy's height, or at least height of the rope from the dock is y. And then the distance of the rope, we'll call that z. So we know that the rope is being pulled at a rate of 3 feet per second. So if I do x, x prime, y, y prime, z, z prime, the length of the rope is decreasing by 3 feet per second. That's how quickly it's being pulled in. So dz dt, or z prime, is going to be -3. I know that x is 30. I want to know how quickly x is changing, so I don't know x prime. Y is 4. And now we have to ask ourselves, is y changing at all? Is this guy moving his hands up or down? And I mean, no, he's not. This should be his fixed stance. So my y prime is going to be 0. And that leaves me with z. But this isn't too bad. We know it's a right triangle, so x squared plus y squared equals z squared. So if I plug in, I'll get 30 squared plus 4 squared equals z squared. So plugging that into my calculator real quick, I'm going to get 916. The square root of 916 is, it's going to be close to 30. It's going to be 30.3 after rounding. So my z is going to be 30.265, but I'm just going to round it to 30.3. And if I'm trying to find x prime, it means that I'm going to take this relationship here and take its derivative, d dz. Or not dz, dt. We're taking the derivative with respect to time. If I do that, I'm going to get 2x x prime plus 2y y prime equals 2z z prime. So if you want, you can go ahead and cancel out all these 2's. And then I'm going to start plugging in. I'm going to get 30x prime plus 4 times 0 will equal 30.3 times negative 3. So that's 30x prime equals negative 90.9. So 90.9 divided by 30 is going to give me, I forgot my x prime. My x prime is going to give me 3.03, and it's negative. So my x prime is, my x is decreasing by 3.03 feet per second. But the answer here should actually be positive. It asks, how fast is the distance between the dock and the boat decreasing? It's decreasing at a rate of 3.03 feet per second. The negative is letting me know that it's decreasing, but I wouldn't say that it's decreasing at a rate of negative 3.03 feet per second. So my final answer is 3.03. Honestly, if you were in my class and you put a negative there, I wouldn't dock you, but some professors might, so just be careful there. And yeah, that's all we got for today. So just some closing thoughts. There was nothing super new here. It was probably our first time working with 3 variables, but I'm hoping that this shows how implicit differentiation can be used. I find the more that you do related rates, they're actually pretty fun because you get real answers. But I'm a little biased being a teacher. I remember being a student and finding these to be very painful. But it comes with practice. The more you do it, the more you're practicing your derivatives, your implicit differentiation, and your problem solving. Like if they don't give you a picture, you need to draw that picture, and that in itself is a skill that needs to be developed. So hopefully the homework isn't too bad. And if you've got any questions, feel free to reach out.